an announcement I'd like to make before we get started. I'm going to be out of town next Monday, Tuesday, Wednesday, and you'll have 2 guest lectures. Mike here up front, who many of you have met in the Student Learning Center, will be giving Monday's lecture, and Wayne will be giving Wednesday's lecture. Anyway, I just wanted to give you the heads up that that's going to happen. We're going to continue with design of experiments today and pretty much cover most all of the topic of design of experiments. And then on Monday, we're going to start on something that's still related to design of experiments, which has to do with chance error. And I'll mention that as we proceed in today's lecture. So things come in threes today. So we're going to learn about 4 different things, each of which has 3 types, or 3 parts. And the first one is 3 decisions that you need to make when you're planning an experiment. I often like to call them 3 elements of an experiment. So we need to answer these 3 questions. What conditions to study? That's what are the treatments and placebo, that sort of thing. What measurements to make? That's the response on the thing you're treating. And what's the experimental material to use? Those are the units, whether they're people or some kind of material. You should be able to take the answers to those 3 questions and put them in a sentence, such as the one I have at the bottom. Sort of fill in the blank kind of question. The experiment compares the effect of these various conditions on some kind of response for these units. Okay, so today we're going to go through 4 experiments, 2 of which you will be the subjects of. And after that, we'll go through all of the different pieces. So one of the experiments is going to be the Salk field trial that we talked about on Wednesday, and we'll simply debrief on that experiment by answering all the questions. So let's answer the questions for the Salk field trial. What were the conditions to study? That was the new vaccine and the salt solution. Those are the 2 conditions. Okay? Sometimes they're called levels of a factor, because you can think of that as data, and there are 2 possible values that every unit could have. One is they got the Salk vaccine. The other is they got the saline solution. So that's a nominal variable or a factor, and it has 2 levels for the 2 possible conditions. What were the measurements to make? In this particular case, it was whether the diagnosing doctor said that the unit had contracted polio or not. So it was sort of a yes-no, polio or not. So again, putting our data hats on and thinking about what kind of data is being collected on every unit, it's whether or not they contracted polio. So again, the response in this case is nominal. And finally, what's the experimental material that was used? And that's the children in grades 1 through 3. So we can construct a sentence of that. The experiment compares the effect of the Salk vaccine and saline solution on polio for children in grades 1 through 3. All right, so another set of 3 is there are 3 sources of variability. Those exactly mirror the 3 decisions that you need to make for your experiment. So the very first source is the conditions. That's the variability you want to see. You actually want to see a difference between the children who got the Salk vaccine and the children who got the saline solution. So that's a source of variability, meaning there's going to be variation in the responses from the 2 different groups. So that's wanted variability. Then there's variability that's due to the measurement process. Depending on the kind of response, there could be measurement error associated with it. That's unwanted variability. And then there's variability due to the material or the units. Some of that we talked about on Wednesday. That might be variability due to income, due to grade level, that sort of thing. And so these are, again, unwanted sources of variability. So a good design lets you try to control for and or estimate the various sources of variability. Okay, so those are the sources. Now, what are the kinds of variability? The first one is the planned and systematic variability. So that's, again, wanted variability, and that's exactly tied to, for example, the kind of variability that you see that's due to your conditions. That's systematic and planned. Systematic means we expect a bias, if you will. Bias isn't necessarily bad in this case, but you expect a systematic difference between the children who got the Salk vaccine and those who did not. Then there's chance-like variability, and that behaves like a random process, like drawing tickets from a box. That's what you're going to learn more about on Monday and Wednesday, is this chance-like variability. Although we might not want it, it's definitely something we can live with. We know how to handle it. We know how to estimate the size of it, and the fact that it's chance-like says that, in particular, that there's no systematic bias in this variability, and so on average it has no effect. Although there is. Well, we'll talk about this more on Monday. There is a difference from what you actually would like to be measuring and what you actually get, but the variation behaves in a way such that on average you do see your true value. Then there's the unplanned systematic variability. So that means that there's something going on here which systematically affects some subgroup of the measurements that you're taking. That's unwanted and can entirely ruin an experiment. If we go back to the Salk trials and think about these three sources of variability, the first one, the planned systematic variability, was something that we wanted to see, and that's a variability from from the treatment group to the control group. The chance-like variability, you can think of that in this case as the random process that we use to assign the consenters in this to either the treatment group or the control group. That's a chance-like variability that, again, we can live with. On the other hand, the unplanned systematic variability we saw in the other design for the experiment, and that had to do with comparing the first and third graders to the second grade consenters. And you saw that the results of that didn't necessarily ruin the experiment, but definitely compromised the size of the effect that you would have seen. Yes? Yes, it is. It is like a confounding factor, a lurking variable. That's right. So there are different ways that we can go about trying to control systematic variability. If we go back to Fisher's experiment, we tried to control potential systematic variability that we didn't want by making sure that the protocols for the experiment were such that you couldn't tell the difference between the Mexican Coke and the regular Coke by things like temperature or amount served or color of the cup, all of those kinds of things which could have introduced a systematic bias. In the field trial, we introduced various sort of precautions to try and also control the amount of systematic variability. The placebo is a way of controlling the bias that has to do with the fact that you're just taking a medicine even if it has no effect. Therefore, they gave the medicine to everyone. The subject blind is a way of controlling for any kind of bias that might happen when someone knows that they're really getting the treatment versus those who know that they didn't get the treatment and therefore are just part of the control group. And again, evaluator blind is a way to try and control for the systematic variability that could enter with a doctor who really might be influenced by the knowledge that the child did or did not get the actual vaccine. The last of the sets of three are three design principles that statisticians use or scientists use to design experiments. The first one's random assignment. So by that, we do not mean a haphazard kind of assignment. We mean a process, a chance process, like the process of drawing tickets from a box. What's really nice about random assignment is that the other kinds of potential systematic variability can sometimes be eliminated by a simple random assignment of units to the treatment or to the control, to the conditions. And so that, in a way, then sort of makes all of the groups, the separate groups that are receiving the different conditions, as similar as possible. And therefore, it evens out any potential systematic variation. Blocking is another way. We'll show examples of that today. Blocking is where you take your group of units and you divide them up somehow, sort them, or you take groups and you cut them up in parts, and you arrange them such that the groups are as alike as possible, and then within each group you assign all of the conditions. So that's when you think that one group, when you think that there's a particular factor that might influence the response. And so if you can then divide your units up into groups that are similar according to this factor, and within each subgroup, everybody, you see all of the different treatments or all the different conditions. So again, getting back to this sort of confounding idea, if this other variable is a potential confounder, that way you're controlling for it by giving everyone who has high income, they all get both sets of Salk and salt solution, and middle income get both sets, and low income get both sets, and you then make comparisons within the groups as well. And the third design feature is called factorial crossing. That's when you might have more than one type of condition or set of conditions that you want to compare. And so what factorial crossing says is, okay, we'll get to an explicit example of this, but it says, okay, I want to look at every different possible combination of levels in each of the conditions. And that's what it means by crossing. So if over here I've got two conditions, that's the salt vaccine, and the salt solution and the vaccine. And over here I've got another condition, and that might be you take that by injection or you take it by pill. And so I've got now two different conditions, and by crossing them, I get all four combinations of vaccine with pill, vaccine administered by injection, salt solution, that's a little hard, I guess by salt or sugar pill, and salt solution by injection. All right, we're going to have a little break here. Our first experiment, you guys are the subjects of. Could I ask you to hand these out this way? And could I ask you to hand these out this way? And we'll see if we need any more than what I've got. So you're about to get a little questionnaire that I would like the answers to. Oh, and he wants one. So don't show it to your neighbor, just fill it out. And when you're done, close it up and pass it over. Did you have enough? So it was exact? You don't have any left over either? Wow. Okay. So when you finish filling it out, pass it to the center and we'll collect them. Thank you. Thanks. Thanks. Can you get it? Thanks. Thank you. Take it. Thank you. You don't have to think too hard about it. You won't be graded on it. Whoop! I almost dropped them all. Thank you. Thanks. Thanks. All right, any left? Yes, thanks. All right, I'm going to just briefly turn the document camera on, and I'll show you one that is not completed. All right. It says, we use the computer to select a random number between 0 and 100. The number selected and assigned to you is 73. Do you think the percentage of African countries in the United Nations is higher or lower than your number? Circle 1. Give your best estimate of the percentage of African countries in the United Nations. Here's another example. We use a computer to select a random number, blah, blah, blah. The number assigned to you is 11. Is anything crossing your mind at this point? I got that. I heard somebody say that. All right. Who got 73? Oh, my. Who got 11? Did anybody get a number other than 11 or 73? So I tricked you a little bit. You actually didn't get a number assigned at random from the computer. You did get a number assigned at random, but by me, and it was only either 11 or 73. This was an experiment. There's some theory that says that even though that's a random number, the fact that I'm most interested in your answer to question number 2, but question 1 sort of leads you to question 2. Question 1 asks you to compare what you think the percentage is to this random number, and if it's higher or lower. And then question 2 says, okay, what's your estimate for this percentage? I don't really even care if you're close to right. That's why I picked something that most of you probably don't know the answer to. You know a percentage is between 0 and 100. Psychologists have found in their experiments that if you're given a high number, like 73, that you tend to come up with a high percentage estimate. And if you're given a low one, you tend to come up with a lower one. So that's called anchoring. So you use the number, any number that you're given as a starting point, and then move from there. So those of you who got 11, you were asked to make the comparison to 11, and you use that as your starting point, and then you had to come up with your estimate. Those of you who had 73, I asked you to use that as a starting point, and then you came up with your estimate. So I will analyze this data later to see whether or not you fell prey to anchoring. All right. I don't even know the right answer. So we did all of this already. So this was studied by Tversky and Kahneman in 1974. And basically, it has very different kinds of situations where people make estimates from a particular starting point, and the initial value affects what their estimate is, even when the initial value is random. The experiment that they conducted is they spun a wheel like that had the numbers from 0 to 100, wherever it landed. They then asked that question, do you think this is the percentage of African countries in the UN is higher or lower than this estimate, than this number, and now give me your estimate. And in particular, they saw that there was a difference between whether you got a high number or a low number. So that's the questionnaire that you filled out. So we can do a little test here. First, raise your hand if you got 11. Okay, now put your hand down if you estimated that the number of African countries was greater than 11. Put your hand down. Right, so most of you, like 80% of you. But then the question is, did you still come in with a lower number than the people who had 73? Because my guess is the people who had 73 all said that the percentage of African countries was less than 73. But then maybe your estimate is going to be higher than the people who got 11. All right, so let's talk about the various pieces of this experiment. What are the units? What are the conditions? What's the response? So it feels like this was a survey, but it was actually an experiment. So we want to fill in this sentence, fill in the blanks. The experiment compares the effect of blank on blank for blank. All right. Anybody want to tell me what they think any one of these are? Units, conditions, response? Yes? Units are people, students in Stat 20. That's right. Okay, good. Yes? Conditions we're having, yes, what we're calling an anchor, and those are, how many conditions did we have? How many factors or levels of our factor? 2, 11, and 73. And the response? Yes, I heard somebody say it. The estimate, or the percentage that you're coming up with. Is that estimate nominal, ordinal, interval, or ratio? Ratio, very good. Wow, I'm impressed. So yes, the experiment compares the effect of an anchor, 1173, on estimates for the students in Stat 20. Terrific. Let's talk about the design principle. The questionnaires were randomly ordered before being handed out. So that was my way of trying to do a random assignment, because it was going to be really hard for me to take everyone here, flip a coin, or somehow put your names in a box, and then when I pulled you out, you got one versus the other. That would take far too long, and oftentimes when you're doing designs for experiments, those are factors that you have to consider when you're doing your design. How much money you have to do it the right way, and how much time you have. So what sort of bias do you think this randomization could have eliminated from the experiment? So basically I randomized the assignment to whether it was 11 or 73. What possible sort of difference could that have made? I've got a few questions. One is, what if I took the front half of the class and gave you all 11 and the back half got 73? Do you think that would make any difference? Are you guys in the back, are you less likely to be paying attention or not? Could that make a difference? I don't want to go there. What if I took the left half of the class and gave them 11 and the right half got 73? Do you think there's a difference between you guys who don't sit next to the windows or are close to the door? I don't know. Or maybe you're more likely to be left-handed than right-handed? Or does that make a difference? I don't know. What about if I'd given all the females 11 and all the males 73? Do you think the females would have worked harder to be more conscientious, to try and get the right answer? I'm not going there either. But the point is that there might be all of these hidden biases that we don't know about. And the randomization process evens that out for us. All right, get ready for your next experiment. All right, you really do need to be paying attention to this. This has a speed element related to it. Get a clean sheet of paper out. So what's going to happen here is I'm going to flash on the screen for it's supposed to be for a half a second. I don't know if I can do it that quickly. I'm going to flash on the screen a set of 12 letters. They're going to be arranged in 3 rows of 4 letters each. You're going to look at them and try to take it all in. And then immediately, I'm going to ask you to either recreate the whole thing, all 12, 3 rows of 4, or I'll say middle row, or bottom row, or top row, and you just write down the 4 that are in whichever row I call out at random. Right? You guys ready? We're going to do this a few times over. You ready? Yes? Okay. Here we go. I'm going to flash it for a second. On your mark, get set, go. Bottom row. Don't really try it. Bottom row. No way? All right. How many seconds do you need? 2? Well, we can't give you so many that you can always get it right. That's kind of the point. All right, I'll give you 2. Now you know it's the bottom row, so we have to throw this one out. Okay, next one. Get ready. Whole set. Just do your best. Are we ready to go to the next one? Are you ready? Yes? All right. Here we go. On your mark, get set. Middle row. One last one. Now you're primed. You're all ready? In the back, you guys ready? Yeah? Okay. On your mark, get set, go. Whole set. Now what I'd like you to do is score someone else's sheet. All right, so pass it to somebody else. And I'm going to give you the answers, or not the answers, but I'll... So just count it right if they've got it in the right position, and the right letter in the right position. So the first one, I don't know if anybody did the first one, but it's the bottom row, which would be ATSQ. The next one, the whole thing, that was the one where you got, I actually gave you more than 2 seconds. RBSC, TYUE, ZXDA. Okay. Believe it, not many people get many right, so that's kind of the point of this. Then the middle row is the third one, which should be DPRA. And then the last one was the whole thing, XVAF, RDMY, EPGZ. EPGZ, right. Okay, I'd like to just have people call out you can give the score now back to the person you scored the results of. And I'd like you to call out in the middle, for those that I'm going to throw out the first trial. Oftentimes we do that in experiments, especially in a manufacturing process, where we'll take repeated measures on some process at certain sets of, temperature or pressure or whatever, and we throw out the first set because that's while the machine's sort of getting ready or getting up to steady state. All right, of the middle, the DPRA. How many people got it all right? 3, 4, wow, okay. About 8, 10 of you. How many people got 3 of the 4? Fewer than all right, okay. How many people got 2? All right, and the rest of you got 1 or 0? Of the whole, let me hear the maximum. I know you guys don't know, but did anybody get 9 right? 1 person, 2 people, wow, I'm impressed. All right, how about 8? 4 or 5 of you? 7? Did anybody get 7 right? No? All right, so it's an interesting theory that these psychologists have been working on as they're trying to study short-term memory. The recall just in a few seconds after you've seen some image flash on a screen. And they have found that when you're given 12 letters, which you guys got, that people only get 4 or 5 right. How many of you got 4 or 5 right? A lot of you. Now, on the other hand, they found that when you see those same 12 letters and are asked to only recall the middle row or the bottom row, that people get about 3 right on average. And we saw a bunch of you got 4 rights, even more got 3, and then 2. So this is a really curious phenomenon, right? If you can get, on average, 3 right out of 1 row, what would you expect people to get out of the 3 rows? 9. Well, there's 3 rows. You get 3 right per row, right? You'd expect 9. But there's something going on in your short-term memory such that you don't do much better when you have to recall all 12. That you actually have a higher rate of accuracy of getting 3 out of 4 when you're just recalling. You're still, I didn't tell you what to look for before I showed you all 12. And you're able to get, on average, 3/4 of them right when I randomly pick a row. But then when I ask you to just give me the whole thing, you get less than 50% right on average. That's pretty curious how our short-term memory works. All right, so what kind of experiment is this? What are the units, the condition, the response? The units, I'll help you there. That's all of you, students in Stat 20. What's the response? Yes? The amount you got right? We can either report that as a percentage. Percentage might be the best way since the denominator's changing depending on whether you're recalling a row or a whole matrix. That's right? Yes? Uh-huh. That's a very good question. The question was, how do you actually score this? Are you scoring it by position or just that you recalled the letters? And I asked you to score by position, but the experiments, I've read the papers, and they don't actually say how they score it. So they could be simply scoring it on, did you recall, how many letters did you recall? Whatever order. And I don't know. And what's the condition? Oh. That's the response. The amount of letters you got right is the response. What's the condition? What was I varying? What was I controlling? Yeah. What? What I asked. That's right. Who said it? I don't know who. I heard a voice. Yes. What I asked. They were how many possible conditions? 4. Whole matrix, top row, middle row, bottom row. That's right. There's a fundamental difference between this experiment and the one we just did with you, the little questionnaire. It's maybe a little subtle, and it's the relationship between the conditions and the units. Does anybody know what that is? It's quite subtle, yes? That might be, that wasn't what I was asking about, though. I was asking, there's a fundamental difference between this experiment and the one with the survey in terms of the relationship between the conditions and the units. Let me ask you a question. How many conditions were there in the survey questionnaire? 2. How many did you get of those 2 conditions? 1. You got either 11 or 73, okay? How many conditions were there in this experiment with looking at the 12 letters? No, there were 4 conditions. There was the whole matrix, the top row, the middle row, the bottom row. There were 4 conditions. How many did you guys I'll pick on you again. How many did you get? You got 4, well, we actually had to throw one out, but you got 4. You got the whole twice and the bottom in the middle. So the difference is here is that each unit, you've already told me the units are the students in the class and with the conditions and the response. So we've filled in this, we've described the experiment in terms of what are the 3 elements, but we haven't described the design structure yet. So the units are the students in Stat 20. The conditions were the top, middle, bottom row, or the whole matrix. The response was the fraction or percentage correct. But there's the blocking structure is one of the, so that's an example of blocking. Every unit got more than 1 condition. Every unit, I could have given you all, if this, in actual practice, people got many of these different top row, middle row, bottom row, many different tries at recalling a row or a whole matrix. So in this case, blocking, each student received all 4 conditions. Now, randomization, ideally, each student would have gotten their own random assignment of the ordering of those conditions. Because we're doing this in a whole class, I couldn't do that. But ideally, we would randomize within each block. So I'm calling every one of you a block. And I've assigned to each one of you multiple levels of my main condition, whole, top row, bottom row, etc. All right, last experiment of the day. And in the past, I have done this in class as well, but it takes quite a bit of time to do, so we'll just go through it. This is another one of these psychology experiments. They're kind of fun. Scientists are interested in studying people's reaction to a shape recognition for tactile stimuli. In other words, can you recognize, in particular, a shape that's being drawn on the palm of your hand? So they were interested in whether it made a difference in how you recognize it if your hand is in this position or this position. So if it's extending from your body or if it's at an angle with your body. That was the thing they were most interested in. Okay. So what in particular were they looking at? They were telling you, I'm going to draw the letter J in your hand. Why don't you stick your hand out? I'm going to draw the letter J in your hand, and you close your eyes. And you need to tell me whether it's a regular J or a mirrored J. Regular J. And what they do is they measure the time from when they've drawn it in the person's hand till when they figure out whether it's regular or mirrored. And that's time that it takes for you to process this tactile shape in your hand. Okay? And then they throw in one more complication because they think that maybe it makes a difference in your orientation as to the orientation of the J, that they then decide to rotate the J through 4 different angles. 0, so I'm rotating my hand. 0, 90 degrees, 180, or 270. And they rotate the J and the mirror J. So I'm going to do this to you again. Hold out your hand. And now I'm going to give you a J that's either going to be at some angle, and it's either going to be J or the mirror J. So you ready? Okay. Oh, you didn't need to guess the degrees. You just needed to tell me whether it was mirror or regular. Which one? It was regular. Good. And so it takes a little longer, depending on if I don't draw it in the way you expect it. So, you ready? Can you tell me what the units were? Basically, it was people. What the response was. I'm going to go to the hardest one last. What's the response? What did I measure? No, that's not what I meant. That's what I determined. Time lapse. I actually didn't care whether you got it right or wrong. But yeah, I wouldn't tell you that in advance. Why wouldn't I tell him that in advance? Because then he could do it really quickly. But it's the time it takes you to recognize whether it's a regular J or a mirror J. Conditions. What were you going to say, Adrian? What you were going to say was one of them. The angle of rotation, 0, 90, 180, 270. That's one set of conditions. That's a protocol for the experiment. Everyone's will always have their eyes closed, so I'm not altering. It would be, and that's why I've asked them to close it. So, very good point. Okay, I have not chosen, whenever there's one thing that everybody has to obey, that's no longer a condition that I'm assigning to different groups, right? That becomes a protocol for the experiment that you must, and that's what the Dr. Poisson didn't do. He broke one of the protocols. There will be a set of instructions, rules. You must close your eyes, you know, that kind of thing. So that's one of the protocols for the experiment. But there was more conditions than just, what was the condition they were interested in? Yes? The position of the hand, that's right. And there were 2 levels to that, in front or to the side. And there were 4 levels to the angle. Were there any other conditions? Yes? Really good point. That was controlled and not a condition. So they only did it on right-handed people. Yes? Yes? Mirror or regular J. So here we have 3 different conditions, one with 2 levels, another with 2 levels, and one with 4 levels. So each subject had the J traced in all combinations of the hand position, symbol, and angle. So they had their hand in both positions, they had the symbol flipped, and all the angles. And every possible combination of that. How many times would I have to ask a subject to do that if they got each one of these once? So I heard it. Somebody said it. Either that or I'm hearing things. 16. There are 16 different combinations. That's factorial crossing. So that's the last piece. So we did all 3 things in this experiment. We randomized the order of assigning each of those 16 possible combinations. We blocked. We gave them all to each person. And we factorial crossed. So we had, 2 hand positions, 2 symbols, 4 angles, total 16 combinations. We blocked on people, so every person got every single condition. And we randomized. Each person got them in a different order. So that's the Those are the three design structures and how they can each lead to very different kinds of experiments. And what you do to design your experiment affects how you go about doing the analysis. In this class, basically we're only going to learn how to analyze the most simple kind of experiment, which is just doing random order, not any of the blocking or the factorial crossing. Well, we might do some factorial crossing. And the reason is because it gets really sophisticated fast, and you need to take a course in design experiments in order to learn how to analyze that data. So that's it for today. Have a good weekend, and I'll see you on Thursday if you come to office hours.